Hello, Assalamu alaikum. How are you all? How's everyone? All okay? All good? All right, great, mashallah. Okay, so yesterday we were doing chemical bonding. We started off with chemical bonding yesterday, and we did ionic compounds and simple molecular structures or simple covalent compounds, basically. So, uh, the basic gist of it is that when we yesterday looked into the ionic compounds, we said that ionic compounds are basically formed between positively charged and negatively charged ions, that is your cations and anions respectively. Okay, and if you look into the properties of ionic compounds, the ionic compounds are usually solids at room temperature and pressure. Simple ionic compounds, we said that they have the how do we find out their formula? We're simply going to swap and drag their valencies. For instance, if we wait, okay. So for instance, if we have magnesium chloride supposedly, okay, so Mg is 2 plus, it is present in group 2 of the periodic table. Chloride ion is present in chlorine is present in group 7, so it forms a chloride ion with Cl negative. Negative 1 is the valency. We're going to swap their valencies and then drag them down. Okay, so this valency will be swapped here, it will be dragged down as a subscript, and this one will be swapped and then dragged down as a subscript. So 1 is usually not written, so we don't write 1 as a subscript with Mg. And with Cl, you're going to write 2 as a subscript. Okay, so MgCl2 will be the formula for this simple ionic compound, that is going to be magnesium chloride. But when you have same kind of valencies, for instance, in supposingly sodium chloride or MgO, magnesium oxide. Whenever there are similar valencies, this is going to become Mg2 plus and O2 minus. So what is going to happen? You're simply going to cancel them out and then write whatever is left behind. So MgO will be written as the simple molecular formula. Okay. Do we have any questions up till now from yesterday's sessions? Any queries? Yes, any questions, any queries from yesterday's class?
Yes, Miss, I have one.
Yeah.
So, is single bond or triple bond stronger?
Triple covalent bonds, they tend to be strong as compared to single covalent bonds.
Okay, because I have learned that the single bond is stronger.
No, triple covalent bonds, they tend to be stronger. In what sense are you talking about? Since this topic is going to go into AS chemistry, and whenever the pairs of electrons they increase, the shared pairing of electrons they increase, what happens that they come closer together. So more energy is required to overcome that energy. So bond enthalpy basically increases. Okay, and this bond enthalpy and everything else is going to come in your chemical energetics, and basically is asked in your AS chemistry. This is not a part of your syllabus.
Okay.
Yeah. Anything else?
No, thank you.
Okay, moving on furthermore, then we discussed properties of the ionic compounds, right? Ionic compounds, they are usually solids at room temperature and pressure. They have higher melting and boiling points, and they are basically good conductors of electricity only in the molten state and in aqueous solutions. Can someone explain why ionic compounds are good conductors of electricity in only molten state and or in aqueous state? Why not in solids? Why ionic compounds are poor conductors in the solid state?
Because there are no free moving ions.
Because they don't have any free moving ions. Yes, very good. Which are going to carry the electric charge. Okay. And in terms of structure and bonding, why ionic compounds they have high melting and boiling points as compared to simple covalent structures?
Because they have stronger intermolecular forces.
Stronger electrostatic forces of attraction. Intermolecular forces of attraction, you are going to refer it to in simple molecular structures or covalent structures. But when you're discussing ionic compounds, Zoya, you will be referring to strong electrostatic forces of attraction. Okay.
Okay.
Okay. Then if you look into the structure of the ionic compounds, they're basically alternating positively charged and negatively charged ions, and all of these these strong electrostatic forces of attraction present between the oppositely charged ions, they're present in all directions. So they create a giant 3D lattice structure, and overall greater amount of energy is required to overcome these electrostatic forces of attraction. As a result, they have greater melting and boiling points as compared to weak intermolecular forces of attraction which are present in simple molecular compounds or simple covalent structures, okay, such as carbon dioxide or water. And water basically, now this topic is going to go in some other direction. In water, you have hydrogen bonds which are present, which is why hydrogen bonds they require more energy as compared to any other structure which doesn't have any hydrogen bonding present. Are you getting my point? There is two different things in covalent structures. Any structure, any simple covalent structure having hydrogen bonds will have greater melting and boiling points as compared to any other simple molecular structure or covalent structure which doesn't have any hydrogen bonds. Is this point clear? Do you want me to repeat myself?
Yes, Miss, could be one more time.
Yeah, okay. So I said basically that any compounds which have hydrogen bonds present in them will have greater melting and boiling points as compared to any other covalent structures which doesn't have hydrogen bonds. Why? Because hydrogen bonds require greater amount of energy to overcome these forces as compared to any other covalent structures which simply have weak intermolecular forces of attraction or any van der Waals forces of attraction. Okay. Next, we move on to we talked about covalent bonds with covalent structures, how to draw them, their dot and cross diagrams. Okay, you can refer to the lecture. I've uploaded them on Google Classroom link. Okay, and next we're going to do today that is your giant molecular structures or giant macromolecules. Okay, so coming to the topic. You basically in your giant macromolecular structures, however, there are various other giant macromolecular structures, but according to the syllabus, you should be covering three basics, that is graphite, your diamond, and silicon dioxide. Okay. So graphite has the structure where, if you look into this, each carbon atom is basically forming three covalent. Carbon actually is present in group 4 of the periodic table. So it can actually form four bonds, okay, four single covalent bonds. But here in graphite, it creates a hexagonal shape, and it forms layers of carbon atoms, or layers of hexagonal rings are formed basically, or carbon sheets are formed which lie one upon each other. And between these carbon sheets or layers, there is weak intermolecular forces of attraction which are present. Okay. This is these dotted lines, they're basically weak intermolecular forces of attraction. However, these solid lines, they are intramolecular forces of attraction. They are referred to as intramolecular forces of attraction. Okay. So when anybody asks you why graphite has greater melting and boiling points, because it has greater amount of the bonds which are present, and these need to be overcome to to completely change the state of matter. Okay, so each carbon atom here is forming three covalent bonds with three other carbon atoms. What does this mean? This means that the fourth electron, which is present in the outer valence shell, or the outermost shell, is basically free to move. So every other carbon atom here has its fourth electron, which is free to move. Hence, it is able to travel throughout the graphite structure, throughout these graphite rings and the layers between the carbon atoms. So, because of this property, we can say that there is a sea of delocalized electrons which is created, sea of delocalized electrons which is created, and hence, as a result, this graphite is the only exception in all of the covalent structures which is able to conduct electricity. Is this point clear so far? Yes, are we clear?
Yes.
Okay.
Yes.
Then these layers basically have, since they have weak intermolecular forces of attraction which are present in between the layers, so which makes graphite slippery, or it makes it soft. It can be used as a result, it can be used in a lubricant or in pencil lead, allowing, which basically allows the layers to slide upon each other. Okay, this characteristic property allows it to have another element of being used as a lubricant. Okay, so if any certain force is applied to one of the layers, they are going to simply slide upon each other. This means that they're very easy. It's very easy to overcome these intermolecular forces of attraction. They'll break apart and then they're going to reform again. So graphite properties include that they are able to conduct electricity. We said that this is the only exception here, that they're able to conduct electricity. Why? Because they have a sea of delocalized electrons which are able to carry electric charge. They're used as a lubricant because these layers, they are able to slide upon each other. The applications involved include that graphite is used in or as electrodes, okay, because of this property. Then they have greater melting and boiling points as well. Okay, moving on to diamond. Diamond has there's one carbon which is covalently bonded to four other carbon atoms. This means that there is no sea of delocalized electrons which is present. Every other carbon is completely engaging its outer valence shell electrons with the rest of the carbon atoms, hence creating a tetrahedral three-dimensional structure. As a result of this three-dimensional structure, you will be able to identify diamond is going to be completely hard because of its strong covalent bonding which is present. Is this point clear so far?
Yes.
Okay.
Yes.
All right. So you need to know, just like I've written very few points here, okay? And these few points, you can elaborate this, you can further enrich these points according to your needs. However, when you're going to solve questions and when we are going to look into past year questions, I will tell you how to approach the questions. Okay, how the examiner wants you to implement this acquired knowledge into the papers. Okay, I will tell you how to decode the questions. For instance, if it's a very long question, okay, you have to decode it, chop it off into certain chunks. Okay, understand it, comprehend it, and then apply all your acquired knowledge to that particular question. Okay, we are going to go through that as well. So diamond, if you look according to the structure and bonding, since it does not have any delocalized electrons, so we would say that will it be able to conduct electricity, yes or no?
No.
It is not able to conduct electricity as a result of no presence of delocalized electrons. Okay, so it lacks delocalized electrons, which is why there is no such particle to carry its electric charge. Only ions and electrons are able to carry electric charge. If that is not present, it is a covalent structure, right? So it does not have any free moving ions, it does not have any delocalized electrons. As a result, it is not going to conduct electricity. Because of its three-dimensional structure, making it hard, it is also used in drill bits, to cut tools, to cut metals. Okay, and it is also used in various other industrial applications as well. Okay, moving on to silicon dioxide. If you look into silicon dioxide's structure, here as well, every blue ball you see, every blue circle you see here, this is a silicon atom. This means that this particular silicon atom is covalently bonded to how many oxygen atoms? Four. Okay, just look into this one right here. This particular silicon, it is connected with or covalently bonded with four other red circles. This means that it is bonded to four other oxygen atoms, making its formula silicon dioxide SiO2. It is also present, it is basically one of the major components of prior components of sand as well. Here, every oxygen atom is bonded to two other silicon atoms. Okay, and this is also a three-dimensional structure. It does not have any delocalized electrons, so this is also not able to conduct electricity. And sometimes some question comes up where they ask you to compare and contrast this, why the properties of diamonds and silicon dioxide, they are same. Can someone tell me why the chemical properties or the physical properties, they are same of silicon dioxide and diamond?
Similar
Because they have the same structure.
Because they have the same structure. And so what, hypothetically, what would you suggest? What would be the physical properties of silicon dioxide?
High melting point and boiling point,
And
and high density.
high density, and anything else? It doesn't conduct electricity. It is going to be hard. Okay, these are colorless crystals, just like diamonds. Okay, so if you compare the properties of diamond and silicon dioxide, both of them, they have high melting and boiling points because of their strong intramolecular forces of attraction. Intramolecular forces of attraction here are referred to as covalent bonds. Okay, tetrahedral arrangement contributes to their hardness and their rigidity. As a result, both of these structures, they're pretty hard. Okay, and they share similar physical properties. They have same energy requirements to break their bonds. Okay, so let's move on to metallic bonding now. Do we have any questions from this particular topic? From the last topic?
Miss, can you overall explain what is a giant covalent structure?
Overall explain a giant covalent structure. Anyone
Yes.
from the class? Anyone from the class who's going to explain what is a giant covalent structure? Yes. Yes, Abdul Basit, Ishal, Misha.
Yes, it is a giant structure which consists of elements covalently bonded together.
Yeah, many different many elements, similar type of elements which are joined together, or more than two different elements, they are covalently joined together, covalently bonded together. Okay, so millions of elements which are joined together covalently to form a giant structure is referred to as a giant covalent structure. So if you are asked to identify or distinguish between simple covalent structures and giant covalent structures, you're going to refer to that in simple covalent structures, you don't have lots and lots of atoms which covalently bond together. But here in giant covalent structures, you have lots and lots of millions of atoms which are covalently bonded together to form a giant covalent structure. Any other questions from the last one?
Miss, you said that covalent structures that have hydrogen, have mean more energy.
The ones which have hydrogen bonds, they have greater melting points as compared to
Yeah,
the ones that don't. Yeah. Yes,
why is that?
because of the hydrogen bonds which are present. Every other bond, just like when we're comparing ionic bonds and simple covalent bonds, right? Or simple molecular structures, we say that ionic bonds, they require more and more energy to overcome their forces of attraction, their strong electrostatic forces of attraction. Similarly, when we go through intermolecular forces of attraction, there are many other intermolecular forces of attraction. There are weak van der Waals forces of attraction, which overall come into the category of intermolecular forces of attraction. Okay, but however, they are basically come under this umbrella of intermolecular force of attraction. Similarly, hydrogen bonds is also one of them. However, hydrogen bonds require much energy as compared to any other weak intermolecular forces of attraction. So any other compound which has weak intermolecular forces of attraction will require less energy to overcome that weak intermolecular forces of attraction as compared to hydrogen bonds which are present in any compound which has hydrogen bonds in them. Did you get my point?
Yes. You also told us that hydrogen basically forms a single bond, right? So didn't you say that single bonds are weaker?
No, you're mixing up two different points. I am only solely talking about the intermolecular forces of attraction. Okay. When I'm discussing about intermolecular forces of attraction, this is completely different thing, and single bonds and comparing single bonds, double bonds, and triple bonds is completely different thing. And if you actually remember my last point from last class, I told that there are intramolecular bonds and there are intermolecular bonds. Are you getting my point? When hydrogen forms one single covalent bond, that covalent bond is referred to as, or is will be subcategorized as intramolecular bond, not intermolecular bond. But intermolecular forces of attraction are weak forces of attraction. Okay, let me remind you this. Wait, let me just draw it so you're able to. Yesterday I told, just for example, if you look into this one, okay, hydrogen chloride gas. Hydrogen is only forming this single covalent bond, right? This is the intramolecular force of attraction. Okay, this is the energy which is required to overcome this particular bond, this intramolecular bond, or this single covalent bond will be referred to as the bond enthalpy. Okay. This is not part of the syllabus. I'm just trying to explain one particular thing here. However, if I say that this is another hydrogen chloride molecule, okay, and in between this two different hydrogen chloride molecules, this dotted line is known as intermolecular forces of attraction. Intermolecular forces of attraction, they are always weak forces of attraction. Okay. But among these intermolecular forces of attraction, which are also known, which are basically present in your covalent compounds, they're not present in your ionic bonds, right? They are present in your simple covalent structures, right? In between different molecules. They are also known as van der Waals forces of attraction. Okay, they are present in polar compounds. They are also present in your non-polar compounds, non-polar covalents, and polar covalents. Now, this is not part of the syllabus; it's completely AS syllabus. Okay, so, and one of them is also hydrogen bonds. Okay, this is not, these hydrogen bonds are not these bonds. These are hydrogen bonds which are the part of the intermolecular bonds. And this hydrogen bond, which is being formed by this hydrogen atom right here, is your covalent bond. Are you getting my point, Zoya?
Yes.
Okay, so this hydrogen bond right here, when we compare these intermolecular forces of attraction, these hydrogen bonds, they require greater energy to overcome as compared to any other weak intermolecular such as van der Waals or in non-polar covalents or in polar covalents. They all require less energy as compared to hydrogen bonds. So any molecules which has hydrogen bonding present in them will be, for instance, in water. Okay, this is a water molecule. All right, this is a water molecule. This is one more example of it. And this is another water molecule. Okay. Now, any energy which is required to overcome this bond right here is going to be the hydrogen bonds which is present. This intermolecular force of attraction is particularly known as hydrogen bonding. Okay, hydrogen bonds which are present. So this is going to require greater energy as compared to any other which does not have any hydrogen bonds. Okay. And within the energy required to break or overcome any of these bonds, this hydrogen which has created this single covalent bond with the oxygen atom is going to be completely different. They are completely two different concepts. Is my point clear to you so far?
Yes.
Okay, so don't mix to both of these things. Okay, moving on to the next one, that is your metallic bonding. So metallic bonding, it basically refers to the electrostatic forces of attraction which are present between the positively charged metal cations and a sea of delocalized electrons. So they create a giant metallic structure or a giant metallic lattice. Okay. When we look into this furthermore, we see that are you guys able to view the PDF? No. The slide is not visible.
Yes, we only see this slide.
Okay, you only see the previous one, right? Now let me know if it's visible.
Yeah.
Yes, okay. Okay, so metals basically consist of giant structures of atoms which are arranged in a regular pattern. Okay, and these are positively charged cations. If you look into this structure, this is completely you see that positively charged cations are present, and they have, since cations, they, or the metal atoms, they tend to form positively charged ions. Hence they have a tendency to lose electrons. Whenever each atom is going to lose their own electron, they are going to form a sea of delocalized electrons. These delocalized electrons will help the metal to carry the electric charge in any physical state, be it solid, be it a liquid, in aqueous solutions, okay, anything. So in liquid phases, in solid phases, metals are able to conduct electricity, and they're free to move throughout their structure, these delocalized electrons, and there is a sea of delocalized electrons which are present within the positive cations, okay, in between the positive cations. Metals can conduct electricity due to delocalized electrons in their structure, and the ability of the electrons to move through the metal is essential for conduction of electricity. Okay, I think you already know most of the things, only just quickly reviewing all of this: malleability and ductility. Now, for instance, the metal layers, when we talk about this, these two different properties, we see that basically these two properties, they are present in metals because of metal layers, these positively charged cations. Okay, if you see that they are actually similar in size. Okay, their size is completely same, it is equal. Okay, they're all same size cations. So when you apply a certain force at one point, these layers, they are able to slide upon each other. As a result, they get this property of being malleable and ductile. That means it can be shaped into different structures, or it can be hammered to form different shapes. Okay, or they can be drawn into wires. So these are the two different properties of metals, and also that they're able to conduct heat and electricity. And whereas any other alloy of metal, where two different metals, they are combined together or they're mixed together, this property will be completely lost. Why? Because in alloys there are different sized cations, different size atoms which are present, metal atoms or metal ions which are present. When one particular atom is like this, another one is a bigger size, another one is another size. Okay, for instance, in brass, what is brass composed of? What is brass composed of? Yes, anybody?
Zinc and steel, zinc and iron.
No, no, zinc and copper, zinc and copper. It is copper and zinc, no? Brass. It is copper and zinc. And steel is iron and carbon. Steel is iron and carbon, and they do two different forms of steel. Okay, there's one is mild steel and the other one's stainless steel. Okay, so if you see here, supposedly one particular metal atom is bigger in size, the other one's is smaller in size. So if you're going to apply a certain force at one point, what is going to happen? They will not be able to slide upon each other very easily. Okay, as a result, they are going to lose these properties of being malleable and ductile. Okay, so alloys, they are much harder, they prevent any deformation as compared to the pure metals. Okay, pure metals, they're actually soft, especially if we talk about group 1 and group 2 metals. Okay, there are group 1 and group 2 metals. Any other metals which are present within the periodic table? Yes, any other metals which are present in the periodic table?
Transition elements.
Transition elements. Yes, very good. Melting and boiling points. Melting and boiling points of metals is going to be high because of their strong electrostatic forces of attraction which are present between positively charged cations and the negatively charged electrons. So more energy is required to overcome the metallic bonds. Okay, so these are different properties of the metals. You will be able to identify when you get a different case scenario where you will be asked to identify any metals. For instance, usually questions, they come up where you are asked to identify which, according to the properties, which one's going to be which particular element. Did you guys have a look at the questions which I PDFs which I sent you yesterday?
No.
No? Okay. Anyone else? Anybody else who had a look at it? Okay, let me just open it up. Wait. Do we have any questions up till now? Any queries? Okay, are you all able to view this PDF? Okay, tell me answers one by one. Which molecule has only two shared pair of electrons? You may write your answers in the chat box, please. Okay, Ryan says water, D, and anyone else? Basit also says T, Ibrahim also says T. Yes, yes, good, 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 good. D is the correct answer. There are two shared pair of electrons here. Okay, in water molecule, single covalently bonded, oxygen and hydrogen, and there are two of those single covalent bonds. Which row describes the formation of single covalent bonds in methane? Methane is CH4. Is it A, B, C, or D? Yes, good. A is the correct answer. Atoms, they basically share a pair of electrons, and both atoms, they gain a noble gas electronic structure. When they're sharing their pair of electrons, they basically they have a mutual sharing of electrons, and both of the atoms must attain a noble gas electronic structure, which is why hydrogen chloride is not an ionic compound. Hydrogen cannot transfer its the sole electron, that is it's only one electron to the chlorine atom. Both of them must have um, mutual sharing of electrons. Okay, then the next question says fluorine is in the same group of the periodic table as chlorine. Which diagram represents the arrangement of the outer shell electrons in a molecule of fluorine? Yes, B is the correct answer. Good. B is the correct answer. Hamdan, look here. If you see here in the next one, there is no complete seven electrons in the outermost shell. This is 1, 2, 3, and 4. But and one is shared here. So where are the two? There should be two more here. Okay. Let's look into another one. Which a covalent molecule M contains a total of four shared electrons? A total of four shared electrons. What is M? How will CH4 have four shared electrons? CH4, Ryan, has 4 shared pair of electrons. 4 shared pair of electrons. 4 shared electrons means 2 pairs. There are 2 pairs. Okay, hydrogen chloride has only 1 pair. Ammonia molecule has 3 different covalent bonds. Okay, methane has 4 different single covalent bonds, and water molecule has 2 single covalent bonds, oxygen and hydrogen. Okay, yes. Yes, moving on to the next one. Methanol, which is CH2O, has a boiling point of negative 19 degrees Celsius. Now, methanol is basically an aldehyde. Okay, this is an aldehyde, and this is not. Oh, so methanol is basically an aldehyde. I don't know why it is not typing. So it is CH2O, which has a boiling point of negative 19 degrees Celsius. Okay, and so they say at negative 20 degrees Celsius, the liquid methanol is a non-conductor of electricity. In a sample of methanol, each atom of carbon, hydrogen, and oxygen, they have a noble gas electronic configuration. So each atom has achieved this electronic configuration in one of the 3 ways, either by gaining or losing electrons or sharing electrons. Which statement do you think describes the bonding between the carbon atom and the oxygen atom, which is present in methanol? Okay, Ryan says A, and Ayla and Abdullah, they're saying B. Can you explain your answer, Ayla and Abdullah? Yes, can you elaborate on your option choices? And Ryan, why do you think that A should be the answer?
I chose A because the carbon atom is in group 4, and atoms in group 4 usually lose or gain 4 electrons.
Okay. So carbon atom here is only sharing 2 electrons here, no? Where are the rest of the 2 electrons? Oxygen is 286. So it needs 2 electrons to gain a noble gas configuration. No, I think you didn't get the option actually. Ayla. The carbon atom, the first option says carbon atom and the oxygen atom share 4 electrons. Next option says carbon atom and the oxygen atom share 2 electrons. And the C and D option says carbon is a negative ion, oxygen is a positive ion. There's going to be no ions which will be present. Why? Because the second statement here says that liquid methanol is a non-conductor of electricity. If ions are present, then in liquid state they must be conducting electricity. But however, they say that there's no conduction of electricity. This means that no ions are present. Okay. There is no presence of any ions. So we completely eliminate options C and D. Now we are only left with options A and B. This means either our answer should be A or it should be B. When we come to this question and we see and we read down the complete statement again, and we look into this molecular structure which they have given us, so we see that this is absolutely correct, Ryan. 4 bonds will be created by one carbon atom. Okay, it is present in group 4. Hydrogen will only form one bond. Okay, oxygen is only going to form 2 bonds because it needs 2 more electrons. Okay, so oxygen is going to form 2 bonds. Now if I look it into as a displayed structure, okay, carbon is this, all right. 2 bonds are created by hydrogen, 1 and 2. This means 2 more bonds are left. So this means those 2 bonds which are left, they will be formed by oxygen to fulfill its own noble gas configuration, and the rest of the 2 bonds which are left for carbon, they will be as well fulfilled for carbon atom. So this is going to be your displayed structure of methanol. This is an aldehyde. Okay, so hydrogen single covalently bonded to the central carbon atom and both of these hydrogen atoms, and here you have double covalent bond with carbon and oxygen. This means a total of how many electrons are being shared in two pairs of electrons. 4 electrons are being shared. A total of 4 electrons are being shared, not 2 electrons. This means our answer should be A here in this case scenario. Did you get my point? Everyone in the class? Carbon can share 4 electrons, so 2 of its electrons are shared with oxygen, and the rest of the carbon's electrons are shared with each hydrogen. Yes, that is right. But why then did you select B as your option choice, Zoya? Your explanation is completely correct, but your choice of option was wrong. Guess, Ryan.
But doesn't it say the carbon and the oxygen only? So isn't B correct?
Carbon atom and the oxygen atom. Tell me how many electrons are being shared there in carbon and oxygen double covalent bond. In double covalent bond, how many electrons are shared?
Oh, 4.
4. So it shouldn't it be A?
Yeah.
Yes. Okay.
Yes, but carbon and oxygen share 2 electrons each.
But they didn't say each. They didn't mention each. This is what I'm trying to explain. That you complete even Ayla, the explanation she wrote is correct, but you didn't get the statement the examiner is trying to say, okay, or convey. They didn't mention each, na? Why are we going to select it then? They said that the carbon atom and the oxygen atom share how many electrons? So obviously they share 4 electrons. If they're going to ask us that how many both of them share equally or both of them share separately, then we are going to tell that they are going to share 2 electrons each. Are you getting my point? Is everyone clear on this?
Miss, then how is it different to the questions we've been solving above?
Sorry, I didn't get you.
We answered the same type of questions like above question, I think 3 or 2. I forgot.
Yeah, okay, let me just scroll up. Let me scroll up, wait. Yeah, which one? This one? A total of 4 shared electrons, for instance.
Yeah,
If you look into the display, if you look into the display structure, what is the central atom here? Nitrogen is the central atom here. It means nitrogen is present in which group?
5.
Group 5. 1, 2, 3, 4, and there is one lone pair. 3 of these, they are going to be shared with hydrogen. Okay. Are these 4 shared electrons? A total of 4 shared electrons? No. These are a total of 6 shared electrons. So this is not the correct option. Hydrogen chloride. You're going to look into the displayed structure. Okay, hydrogen chloride. This is one pair. One pair means how many electrons are shared? A total of 2 electrons are shared. 1 electron by each atom in this covalent bond. Clear? Methane. Carbon has 4 electrons, valence electrons. 4 of them, they are completely shared by hydrogen atoms. So a total of how many electrons are shared? A total of 8 electrons are shared. Water. Oxygen is the central atom. Hydrogen here. Okay. And this is going to be your single covalent bond. Single covalent bond always shares 2 electrons. 1 electron each. 2 shared electrons. 1 electron by each atom. And there is going to be 2 lone pairs in oxygen. So a total of how many shared electrons are here? This is the shared pair. This is the shared pair. Total of 4 electrons are being shared. So obviously D is going to be the answer. Am I clear?
Our answer was C. We all chose C.
Where? Who chose C? For methane? For this particular question? No. I said this for this one. Yeah, I said for this one option D is correct. Water is going to be the correct answer here.
Okay.
Yeah. C is not correct here. If they ask you particularly 4 shared pair of electrons, 4 shared pair of electrons, a pair means 2 electrons are shared. If they ask you 4 shared pair of electrons, then you're going to mark C. Okay, then your option choice would be C. That would be correct, absolutely. But here they didn't ask for pairs. Okay, this is, you have to look into the question again and again. You have to look into the context of the question. Is everybody clear about this? Do we have any particular queries regarding this particular question? Hamdan, Rayan, Zoya, Misha, Ibrahim, Ishal, Ahmed, Abdullah, Basit, and Ayla.
Miss, could you please go to the question below this?
Yeah. Yes, this one.
Yes.
Hmm.
I just have one question.
Mm-hmm.
Actually, never mind.
Sorry?
Never mind.
Why? Ask your question, Rayan. What happened?
If the carbon's electronic configuration is 2 4, right?
Hmm.
And it needs to gain 4 electrons.
Hmm.
If it has already gotten 2 electrons from hydrogen, it only needs 2 more, right?
Hmm.
Then why is it getting 4 electrons from oxygen?
It is not getting 4 electrons from oxygen, no?
Like, why is
It is only getting 4 more. It is only getting 2 more electrons from oxygen. It only has its own. If you look into the dot and cross diagram for this, let me just share the dot and cross diagram as well, so that I can better explain you this. Wait a minute. So this is your carbon. Let me have it. This is your carbon. Okay. This is your hydrogen. This is another hydrogen. This is oxygen right here. Okay. Now tell me that this 2 electrons are already shared with hydrogen. This means that the hydrogen's noble gas configuration and both of these hydrogen's noble gas configuration is completely fulfilled, right?
Yeah.
Okay. Now there are 2 electrons of carbon which are left. This means that 2 of these electrons must be shared with 2 other electrons of oxygen. Okay.
Okay.
Okay. So, and oxygen has a total of how many electrons? 6. 2 of them are already shared. This means 4 are left as unshared electrons, right? 1, 2, 3, 4, 5, 6, 7, 8. Oxygen's complete valency is fulfilled, and carbon's valency is also fulfilled. 1, 2, 3, 4, 5, 6, 7, 8. Right?
Yeah.
So how is oxygen sharing its 4 electrons? Oxygen is only sharing its 2 electrons.
Yeah.
Okay. This is the oxygen's electrons. 2 of these crosses, they are oxygen's electron. 2 of these dots, they are carbons. Now come back to your question again. Repeat your question.
What? Oh, okay. I get it.
Now you get it? Okay.
Yes.
All right. I think we should end the session till here for now. Now you have other classes as well. So inshallah, we will have our next discussion next week. And I believe tomorrow is your quiz as well, live quiz, which will be shared by Miss Maria on Google Classroom. And it is, I think it is 6 p.m. Pakistan time. Also, the topics, I will send it to you on WhatsApp. Okay. Up till now, whatever we have done completely, I'll take a quiz of that. Okay. Take care. Allah Hafiz. Thank you.
Allah
Allah Hafiz.
Hafiz.
Allah Hafiz.